Swayam Prabha. Digital India. Educated India.
Welcome back, friends, to another session of fluid mechanics and rate processes. We've been looking at potential flows. So first we started looking at some very basic flows. Then we got to superposing some basic flows into slightly more complicated flows. We looked at the doublet, we looked at the Rankine half body, and today we are going to look at a very special flow past a circular cylinder. So again we will start with the potential flow and then see why it does not replicate some of the features of a real flow. So we will make some comments about that as well. Flow past a circular cylinder, and the first thing we want to look at is the potential flow. Just to remind you, the potential flows that we are looking at are inviscid, irrotational, and in this course we are mainly focusing on incompressible and also steady. Okay, so it's very special cases. Okay, so we are going to first talk about superpose uniform flow and doublet. I showed you in the last session that we could get a doublet by bringing in a set of source and sink. So the idea was that the source squirts out fluid, the sink collects it, and they become very close to each other, and then the strength also increases to a very large extent, such that the strength times the distance between them is a finite quantity. That gives rise to a doublet. So here is a uniform flow. This is aligned with the x axis, and here it is, I have the axis itself, x and y, and I am going to put a doublet here. So the doublet, as we so this is the doublet and uniform flow. Okay, so the resulting phi that I could write is the superposition of the uniform flow. So this phi, if you recall, was given as ux, okay, and the psi can be written as u times y. And for a doublet that is located at the origin, I had given you the expressions. The phi is given as m by r cosine theta. So the polar coordinates are more suitable, and similarly the stream function was minus m by r sine theta. Okay. Now if I want to do a superposition, I simply have to add the two phi's and the two psi's. So let's do that. Phi would be given as u times x for the uniform flow, plus for the doublet m by r cosine theta, and the stream function is given as u times y plus, in fact I would have a negative sign here then, m by r sine theta. That is it. So I can now get the potential and the stream function for the combined flow. If I want to get the equipotential lines, I have to put this function as a constant and by changing the value of the constant I would get different potential lines. Similarly, to get different streamlines, I would take the right hand side of this function and keep that equal to constant. Different constants would give me different streamlines. Okay, so let us work on this a little bit. So, first I would like to get the two components of velocities. So, if I look at v, I could write that as Vr Er plus V theta E theta. And we have already talked about our convention. The convention is that if this is my axis, the x and y axis, and I look at any point where I am interested in the speed, and this is my r, the vector, this is theta. So, the decomposition is such that I can talk about a unit vector Er, which is radially outward, and then the theta, E theta, is a unit vector in this direction, and Vr and V theta are the velocity components in this direction. So, I could get a velocity vector in the polar coordinates, or I could also get them in the Cartesian coordinates as Vx and Vy. Okay. Now, what I will do is I will try to estimate the phi, for example, and then get the velocity components from that. So, Vr, for example, is given as del phi by del r, and V theta is given as del phi by del theta with, of course, a 1 by r in it. All right. So, this would give me del by del r of, this is my phi, ux plus m by r cosine theta. So, I could write this as u times x is actually r cosine theta plus m by r sine theta. And similarly, this one would be 1 by r del by del theta of u r cosine theta plus m by r sine theta. I am sorry, I made an error here. This should have been cosine theta. Okay. So, I am looking at phi, which is m by r cosine theta. Okay. So, so Vr, if I work it out, I could take cosine theta outside and do a derivative with r. So, I would get the following: u times 1 minus m by r square and u cosine theta, and likewise for V theta I would be able to get, this is minus u 1 plus m by u r square sine theta. Okay. So, these are my components of velocities everywhere. Okay. How about the stream function? Because that would help me draw the streamlines. So, I could also get the stream function, and the stream function here would be essentially u times r sine theta minus m by r sine theta, and this equal to constant would lead to streamlines. I will be using this. So, let me put this on the blackboard. Okay, so the first thing that we want to understand is, what about the stagnation points? Does this flow have any stagnation points? So, first question is, the stagnation points. So, these are points where Vr is 0 and V theta is 0. So, the fluid comes to rest. Intuitively, you can feel the following. There is a doublet which is present at the origin, and then there is a uniform flow. As you know, the effect of the doublet is varying as 1 by r. So, if I go far away, I should not see an effect of the doublet, and therefore, I should just see uniform flow everywhere. But as I get close to the origin, of course, the doublet is going to be significant. So, the stronger my m, the stronger the strength of the doublet, the larger would be the region where the doublet would be important. If m is small, then of course, compared to u, then I would have a smaller effect of the doublet. Okay, so, the stagnation point essentially is also representing what is the effect of the doublet on the flow. So, there are many effects, this is one effect. If the doublet is not there, then clearly this flow does not have any stagnation point, it is a uniform flow everywhere. So, let us put in Vr and V theta equal to 0. Okay, so, these are the expressions, and so let me call this as 1, let me call this as 2. So, Vr equal to 0 gives me that r square is actually m by u, or I must have cosine theta equal to 0. Okay. The second equation tells me that my r square is equal to minus m by u, and sine theta is 0. Okay. Okay. So, clearly from this we can see that sine theta must be 0. Obviously, you cannot have r square to be minus m by u. Okay. So, if sine theta is 0, so then this condition implies that theta is equal to either 0 or pi. Okay. And clearly, if I put theta equal to 0 or pi, then of course, I do not have cosine theta equal to 0. So, this condition I do not use, and I get r square equal to m by u. So, I will now define m by u as r square, okay, and of course, r is equal to plus minus r, okay, for stagnation point or at stagnation points. So, essentially what I am saying is that if I draw the axis, this is the x axis, this is the y axis, then there are these 2 points which are the stagnation point, and they are located at r r. And of course, there is a doublet in here, and so on. And of course, there is a uniform flow coming in. What about the stream function? Let us calculate psi at the stagnation point. So, this is my definition of the stream function, and clearly if I put the r equal to capital R and theta equal to 0, then I see that the stream function goes to 0. So, what this means is that the streamline that passes through the stagnation point corresponds to psi equal to 0, and that we will call as the stagnation streamline. So, to get the stagnation streamline, all I have to do is put psi equal to 0, okay, which means that I need to put this function equal to 0, and that would be simply u r times 1 minus r square by r square sine theta equal to 0. So, if I somehow evaluate this function, then I get the stagnation streamline. Okay, so this will have different solutions, and the way I can look at it is I can take a particular value of r and evaluate the theta at which this function is satisfied, or conversely I could take different values of theta and see what is the value of r. In any case, if we do that, we are going to get the stagnation streamline. So, maybe I should draw it with a red color. So, my stagnation streamline would actually be a circle. This would be my stagnation streamline. Okay, you can check. All right. And the streamlines around it would of course be not the stagnation streamlines. You can see they would actually look something like this. And on the outside, they go around. Although I have not drawn it, but there is symmetry about y axis. Okay. So, the flow apparently is reversible. Okay. So, whatever is the flow I get in the forward direction, okay, about x equal to 0, then I could just take a mirror image and get the same flow on the other side. Okay. And in particular, I have drawn the stagnation streamlines, and in white color are all the other streamlines. Okay. Let us look at how I define my Vr and V theta now in general. So, having used this relation that r square is m by u, so I can rewrite 1 and 2 as the following. So, Vr is given as essentially u times 1 minus r square by r square cosine theta, and V theta is given as minus u 1 plus r square by r square sine theta. Okay. Now, I could ask myself, what does this flow resemble? So, as we have discussed before, that by definition a streamline means that flow does not cross it. So, I could take any of these streamlines and replace that with the surface of a solid body. What I will do is that I will take this streamline, which is the psi equal to 0 streamline, the circle, and replace this circle with a solid body. So, replace circle with solid body. And what that does is, then I am able to have a model of flow past a circular cylinder. But mind you, this is the potential flow, where the fluid is supposed to be inviscid. So, the argument that is being made is that if I replace this with a solid body, then even though the doublet was there in the initial model, and of course it still exists as far as my definition of velocity, potential and stream function is concerned. But you know, this mathematical expression now resembles as if I am looking at flow past a circle. In fact, you could also argue that if I am only interested in the upper plane, then this models flow past half a cylinder. So if I had some kind of a dome, okay, and I wanted to study what is the flow over a dome or a hut in the context of a breeze or a storm, I could use this model. Okay, it has its own limitations, but nevertheless it is a fluid dynamics model. For that matter, I could even take some other streamlines and replace that with the surface of a solid body. But we are interested in a cylinder, so we will do that. Now the next thing we want to ask ourselves is, what about the properties of the flow on the surface of the cylinder? So surface of cylinder. So clearly we are first interested in the speed, and then we would be interested in the pressure. So let us evaluate Vr and V theta. Okay. So Vr, I would substitute R equal to capital R, and that would be 0. And V theta, as you can see, if I substitute R equal to capital R, then I get minus 2u sin theta. Makes perfect sense. Okay. If I had a circular cylinder, then what is being said is that on the surface of the cylinder, my normal velocity should be 0. Okay. I cannot have a flow going inside the surface of the cylinder. So Vr equal to 0, therefore makes perfect sense. What about V theta? So if you recall, if I look at a certain point here, okay, then this is my direction of Vr and this is my direction of V theta. So the negative sign simply implies that actually the flow would be in the opposite direction. Okay. So I would have, because my uniform flow is from left to right, so at this point in fact I should have a velocity vector pointing towards in the clockwise direction. So that takes care of the negative sign. At theta equal to 0, this is theta equal to 0, I would get Vr equal to 0 and also V theta equal to 0. So these are stagnation points. So theta equal to 0 and theta equal to pi will give me stagnation points. So theta equal to 0 and pi are special points where Vr and V theta are 0. And V theta is maximum at the shoulders. Okay. So V theta equal to pi by 2 is minus 2u, and V theta equal to minus pi by 2 at theta equal to minus pi by 2 is actually given as 2u. So this is interesting. What we are saying is that there is a uniform flow and it tends to get a 0 speed at the stagnation points, and then as the flow goes over the surface of the cylinder, okay, its speed increases from 0 to twice the free stream speed. So actually the fluid element undergoes a fairly severe acceleration, 0 to twice the speed, and then it again goes through a deceleration and goes back to a 0 speed. Okay, so that is on the surface of the cylinder. We can also use the Bernoulli's equation now to calculate the pressure on the surface of the cylinder.